Good morning, everybody, and welcome to today's webinar, Functional Safety and Reliability within Product Development and Asset Management. And now I will hand over to the main person and host today, Simon Carles.
Thanks, Caro. Hi, everybody, and welcome to my webinar, where I'll present an overview as to the role and benefits of reliability engineering and functional safety within product development and asset performance management. This webinar is aimed primarily at those who have only a little or no experience of reliability or functional safety engineering. It doesn't provide any complex mathematics or subject theory, but does focus more on the process and application of the techniques to gain better performance. My name's Simon Carles. I'm a business development manager at Wild Analysis, and I've worked in commercial roles in the field of technical and manufacturing engineering for over 30 years. If you have responsibilities for achieving functional safety and/or reliability performance targets on your product or assets, if you recognise that you need to bridge functional safety and reliability skills gaps that exist in your business, or if you need to keep your competition at bay by enhancing your functional safety and reliability capability, then this webinar will help by providing information and use case studies to illustrate our experience to help you to comply with ever-demanding legislation and bid requirements, achieve better assured functional safety and reliability performance, be more efficient, save money and get product to market quicker, and protect your business brand. I'll provide a brief overview on PDS Vision and Wild so that you can understand how functional safety and reliability supports the bigger digital transformational journey before spending time on two aspects of reliability engineering. The Design for Reliability, or DFR, thread used primarily by companies whose main business is the design, production, and shipping of product, so for example, a medical device manufacturer, and the Asset Performance Management, or APM, thread used by organizations whose primary business is the operating of assets, for example, a wind farm or a bank's data center. I will be referring to ReliaSoft as our solution for these digital threads. We'll then discuss the role of functional safety, the typical industry standards relevant to automated activities, and we'll share a couple of examples to show how functional safety has been embraced. I'll be referring to ANSYS as our solution for the functional safety digital thread. So I'll start at the corporate level and provide some context as to the strategy of PDS Vision. There are three major market trends that PDS Vision has observed. A significant global worker shortage, businesses are facing more risk and cost pressures, and digital disruption. So what I'll share with you today will illustrate how our solutions will make you more efficient with the right digital tools for reliability and functional safety. Now, as part of its growth strategy, PDS Vision acquired 3 engineering software solutions businesses in the last 12 months, Wild Analysis being one of them. We have a wealth of experience in engineering simulation to support engineering design and manufacturing processes, but we also have a significant functional safety and reliability engineering activity. So in the chart shown, Wild's contribution to PDS Vision is the line in purple. It shows how we engage with our clients throughout a product's lifecycle. Wild's engineering simulation solutions fall into 2 main categories: simulation for design and simulation for manufacture. So for the structural analysis, fluid dynamics, electromagnetics, thermal management, acoustics, system modeling, and building physics, we offer those solutions using ANSYS as our main solution. We also use a product called Bentley Plaxis for our geotechnics work. For simulation for manufacture, which includes specialisms such as plastic injection molding, where we use MoldX 3D. We supply deform for metal forming and heat treatment solutions, and ANSYS for additive and 3D printing work. So to complement our engineering and manufacturing simulation solutions, Wild has, over the past 15 years, developed a risk management offering, focusing on functional safety and reliability. There are 4 key facets offered: functional safety, where we provide ANSYS Medini solutions; human factors, which is primarily a consultancy and training activity; and then design for reliability and asset performance management, where we promote ReliaSoft activities. So what is reliability engineering? Reliability engineering is a design engineering discipline that applies scientific knowledge to assure a product will perform its intended function for the required duration within a given environment. This includes designing in the ability to maintain, test, and support the product throughout its total life cycle. Reliability engineering covers the analysis of reliability, maintainability, and availability of a product. Reliability analysis is the application of tools and techniques to examine the reliability of the product or system from different perspectives to determine possible problems and assist in analysing corrections and improvements. An effective reliability analysis is when there is a holistic approach to reliability within a business. We're not talking about having silos of engineers doing individual spreadsheet calculations. So a product is reliable if it doesn't fail. Failure-free state can only be achieved if failure is prevented from occurring. So what is required to prevent failures? We need engineering knowledge to understand failure mechanisms. We need management commitment to mitigate or eliminate them. Proactive prevention should be the focus of reliability engineering. So design for reliability, which is designing a system to be robust and fault tolerant, and asset performance management to maintain items to keep them fault-free state. What is not reliability? It is not reactive failure correction or failure management. Reliability engineering should not be playing the numbers game. This helps no one in the long term and can have very negative consequences. Reliability engineering is weak on absolutes, but strong on trends and comparisons. So, for example, is design A better than design B? So the objectives of reliability engineering in decreasing order of priority are: 1, to apply engineering knowledge and specialist techniques to prevent or to reduce the likelihood or frequency of failures. 2, to identify and correct the causes of failures that do occur despite the efforts to prevent them. 3, to determine ways of coping with failures that do occur if their causes haven't been corrected. And finally, to apply methods for estimating the likely reliability of new designs and for analysing reliability data. There is a 5th option, which is the default position, which is do nothing, but that helps no one. Now, ideally, we would jump straight to 1, but usually there's a need to work up lessons learned at each step to help us understand how to prevent failure. Now, I usually start with 2 key questions. Question 1, do we know how our product fails or how it can fail? And question 2, are we recording failures that occur, either in the field or in the lab, which should inform question 1. Now, reliability engineering touches on and should influence most disciplines within a business. It can be its own department, or it might be within a design department, a maintenance team, or part of the quality group's activities. Here are some typical disciplines that overlap with reliability engineering. There are others as well, such as procurement, where sometimes they might want to involve reliability engineering, particularly when buying complex equipment that has to exhibit particular reliability or maintainability characteristics. So in the product lifecycle, you can see that I've highlighted a number of phases from concept all the way through to product disposal. And the design for reliability discipline that refers to the process of designing reliability into products in order to ensure customer expectations for reliability are fully met and minimize costs and increase profit margins. And this DFR process tends to happen quite early on in the product lifecycle process. Asset performance management, or APM, is a subset of asset management and refers to the way that existing assets are operated and maintained in order to optimize uptime, optimize maintenance costs, and increase safety. And more often than not, the APM process tends to happen post-distribution and installation and operation phases of the product lifecycle. So I've listed a few questions here that are typically asked about where DFR plays a part. So in the design for reliability thread, some typical questions that may arise include: what is the expected life of equipment? What are the major failure modes? What impact do these have? Is it catastrophic? Will the system keep working for a while? How many failures are we expecting from now to the end of the year and perhaps next year? And how might this affect our warranty strategy? How much is it going to cost us to support this product? Are there ways we can keep maintenance costs down whilst maintaining desired reliability performance? How can we make the product more cost effective? Is our product exceeding its reliability targets? Can we source a component or sub-assembly from an alternative supplier? If so, how can we assure no drop in reliability performance? So I'll go on to the questions that might arise within the APM thread. Is the asset performing as expected? Is it critical if it fails? Should I leave the component or should I replace it? Has anyone experienced this before? Does our fracas system have a record of similar failures and what was done to fix the problem last time? Is the root cause of the potential problem understood? Again, has this been captured in our fracas system? Should I consider changing the maintenance plan? Am I doing too much maintenance or perhaps not enough? Should we redesign the component or process? If so, how will I understand the reliability and safety implications of any redesign? So I've got a list here of some common motivations that we've experienced with our clients over the years. The first one is quite a common one, which is to comply with requirements from the client's customer. Often there is little internal understanding of what the requirements mean. So customers being asked, well, your product has got to achieve an MTBF of so many hours or so many cycles. How on earth are we going to achieve this? We need to understand our in-service issues. Maybe there's a large amount of warranty returns. Is there an issue with this component? Would a life data or warranty analysis help? We want to develop internal reliability capabilities. So we want to be self-sufficient. We want to show our clients that we're in control when a failure does occur, or that we want to be on the front foot. We want to improve a product's design. Maybe we want to improve its reliability performance, or maybe it's over-engineered. We want to get to market quicker. There are reliability engineering techniques that are used to develop accelerated life testing, so to reduce the testing time before making product, so products can get to market even quicker. Some companies want to fill a lack of internal capabilities by outsourcing some work, so companies like Wild can help clients. Clients want to make certain that their products are being assured. They want to have confidence that it's going to perform the way it's supposed to do. They want to help win business by demonstrating to their customer that they can confidently demonstrate how their product is performing now, and also how to predict how the product will perform in the future. And finally, but by no means least, a lot of our clients want to control costs, whether it's keeping stocks of spares to a minimum, optimizing maintenance cost plans, or being proactive rather than being reactive. Next couple of slides are really just some data sources which you can take away when you download the webinar. So there's a series of standards that are commonly used in reliability, and then there's a list of failure rate databases and prediction standards that might be of use to you. So I just wanted to kind of summarize a little bit here, which is there are 3 important statements that summarize the best practice reliability philosophy of successful companies. So reliability must be designed into products and processes using the best available science-based methods. DFR and APM practices must begin early in the design process and be well integrated into the overall product lifecycle. But the most important one for me is knowing how to calculate reliability is important, but knowing how to achieve reliability is equally, if not more important. So here's a typical DFR process showing the key phases of a product's lifecycle. Within each phase, from concept to support, the various reliability engineering activities are listed. I won't go through them in detail, but again, you'll have this when you download the webinar. And there's a similar diagram here, which is an overview of the APM activities, showing the key phases of a product's lifecycle and the typical activities within each phase. Now, within reliability engineering, there are a number of tools that are typically used to help develop the reliability program that might be required. So here's a non-exhaustive list of typical reliability tools. This figure illustrates the different groupings of tools. Some are to collect data, such as FRACAS and FMEA. Some are to analyze data, such as live data analysis and reliability growth analysis. And some are to construct predictive models, such as system reliability or unreliability modeling. Now, as I've mentioned earlier on in this webinar, Wild is a ReliSoft solution provider and has been so for 15 years. So ReliSoft is a reliability software for product test, design, and maintenance optimization. It empowers engineers in the reliability domain to transform data into decisions, providing a suite of powerful tools for reliability and maintainability software solutions. You can see products there that are within the ReliSoft suite, from Wible to FRACAS there, ex-FRACAS there. And the products include live data analysis, accelerated live testing, system modeling, RAM analysis, reliability growth analysis, FRACAS, FMEA, and RCM analysis, all to achieve and improve reliability of products, processes, and optimize maintenance planning. The software works for the individual or for an enterprise on a common database platform, fully scalable, using common methods, techniques, and datasets to ensure a comprehensive, fully integrated approach to reliability engineering. I've got 3 or 4 case studies to look at here of where we've helped customers in the past. So a train carriage wash system manufacturer was awarded a contract to deliver a wash system for a UK rail depot. They approached our reliability engineering team to perform a RAM analysis. And the project aims were to demonstrate system RAM's compliance, avoid train wash unavailability penalties, and enable clients to determine optimum maintenance plans and spares levels. And the important thing here is that the unavailability of the train wash system can be financially painful, as there are strict penalties for dirty trains entering service. So we did this work by doing some consultancy work using ReliSoft RAM modules. We identified potential product failures. We produced system availability calculations, and we developed a maintenance task analysis for the client. And the benefits were able to demonstrate full RAM's compliance to the end customer, allow the client to control maintenance costs, and help both DFR and APM aspects of future train wash projects. So for the past few years, this is another case study, Wild have supported clients who specialize in the design, development, and construction of prestigious data centers. Each data center is different in configuration, complexity, and location, and its guaranteed availability or uptime performance can be classified from Tier 1 to Tier 5, where Tier 5 is 99.999% availability. That equates to a downtime of 5 minutes 15 seconds in a given year. The 3 major principles to ensure high availability are no single points of failure, reliable crossover failover points, and failure detection capabilities. Now, Wild used ReliSoft BlockSim for availability modeling and ReliSoft XFMEA for performing the FMEA work. So the benefits of all this is that as availability or uptime is the most important metric for service level agreements, Wild's reliability team were able to provide design guidance and performance feedback to our clients' design teams and enable them to satisfy their clients' SLA requirements. Now, since 2017, Wild have supported major defence OEMs businesses with ReliSoft solutions to ensure that the OEMs met their contractual obligations with the UK Ministry of Defence. The OEMs have invested in a ReliSoft suite of software for AR&M calculations and DRACAS functionality to meet their DEFSTAN 0042, 44, 45, and 60 obligations. Wild provided the software, the training, and the configuration of the software to ensure that the software integrated into the client's processes and data flows, and that the users were getting the best out of the tool features. The integration involved defining or modifying the processes around the functionality of the software. The approach was that we utilized the ReliSoft CRS tokens and ex-FRACAS license solutions. We configured and implemented software into clients' data flow and processes, and we imported legacy data into new ReliSoft databases. And we were able to demonstrate the client's compliance to UK requirements, All our clients have now common tools and methods, and we've provided AR&M confidence throughout the product lifecycle. The case study here is for a cable manufacturer, a European manufacturer of a variety of power cables used within a variety of industries. And this company had a UK manufacturing capability. But they had an opportunity had arisen in the UK rail sector with Network Rail for the supply of signalling power cable. Network Rail expected cable manufacturers to demonstrate that they complied or were in the process of complying with their design for reliability requirements for sourcing selection, as specified by their standard NR L2 RSE 0005. The client approached Wild to support them in their bid process. So our aims were for the client to achieve product approval for Network Rail and also to develop an internal DFR process for generic product development. So we undertook an initial gap analysis to identify what the program scope needed to be. We created a DFR process for the client and then created submission documentation for Network Rail. The output of all this was that the client gained Network Rail product approval. They have now since secured several contracts from Network Rail that they weren't able to before, and they've gained significant knowledge on how to use that knowledge into other industry applications rather than just rail. Now here's a case study for a medical equipment OEM. So we've been working with a major medical equipment for 5 years or more. And in that time, Wild has developed a series of ReliSoft point solutions into an enterprise solution, enabling better connectivity, and is currently working with the client to develop our reliability logistic modeling capability to help reduce cost of repairs and replacement parts. One of the key drivers for the OEM is to minimize the cost of equipment downtime at hospitals, which can incur significant financial penalties. So you can imagine where there's complex equipment that might be in an operating theatre at hospital, and if that equipment keeps failing, then that theatre is unusable, and there are severe financial penalties in such a case. So the aims were to improve reliability capability in the business as overall, to drive down the costs of repairs and spare parts holding, and also to minimize equipment downtime at client facilities. So we used a complete suite of ReliSoft software, including consultancy and training. We hosted a series of FMEA workshops to help our clients understand the process and also how to understand how their product performs or could fail. We developed and enhanced their fracas capability to include costs from bad actors. And also we included a costing modeling activity within their system reliability models to give them more value. And the benefits of all this is that the design team have the right reliability predictive toolset. They're using common tools and methods across all client sites. They have enhanced the effectiveness of business reliability procedures, and they've minimized client penalty charges and repair spares costs. So apologies for the takeaway pictures, but the key takeaways from what I've just been talking about is that reliability engineering is about more than just numbers. It's about the process. It's about a preferable top-down approach to reliability. A proactive approach at an early stage of the product lifecycle will always be less costly and more effective than reacting to failures. Creating a well-defined system definition is essential prior to analysis. There are many tools and techniques that can be used. ReliSoft connects these solutions for significant efficiency gains. Motivations of the client drive the focus of the projects and dictate which tools and techniques should be used. And ReliSoft is the tool of choice for reliability engineering applications and is our digital thread. So I'm now going to go on to our functional safety discussion. And so we start with what is functional safety. So the objective of functional safety is freedom from unacceptable risk of physical injury or of damage to the health of people, either directly or indirectly, through damage to property or to the environment, by the proper implementation of one or more automatic protective functions, often called safety functions. A safety system, often called a safety-related system, consists of one or more safety functions. Now, it's important to distinguish between technical safety and functional safety. Technical safety is passive. Technical safety addresses the nominal performance of functions in order to avoid the risk of harm during normal operation. Now, functional safety is active. It addresses faults and malfunctions and tries to avoid or detect them in case they have the potential to cause harm to humans. So in the example of a lift in that image I'm showing you there, the doors of a lift provide technical safety, whereas the sensors, logic controller, and mechanisms that control the opening and closing of the doors provide functional safety. Functional safety systems are typically comprised of three elements: sensors, logic solver, and actuators, and involves one or more of electronics, electrical, electromechanical, and software. There's a couple of examples shown here, which is a power steering control mechanism and a fluid control valve. Now, IEC 61508 is a basic functional safety standard used as the foundation in all industries and was first published in 1998. It seeks to define the rate of occurrence of failure and the consequent severity of a failure occurring. In the 1970s, incidents in Europe were occurring that had a major impact on the health and safety of the general public and the environment. So a couple of examples are Flixborough in 1974, where there was an explosion at a chemical plant close to the village of Flixborough, which killed 28 people. And the Seveso disaster in 1976, where there was a release into the atmosphere in Italy of a dioxin by a chemical manufacturing plant, which had a major impact on the local environment, where up to 80,000 animals had to be slaughtered. Incidents such as these highlighted the fact that there was little formal guidance and standards for the hazard assessment of process plant. There was already guidance from the Health and Safety at Work Act, and in parallel with the Seveso Directive and the adoption of the Machinery Directive in support of CE marking, all led to the creation of IEC 61508. Now here's an example of typical standards and their enforcers from around the world. Our customers need to comply with the regulators who enforce these standards. And depending on where you or your customers are and which industry you work in, there are various standards you will need to follow. So from the initial publication of 61508, numerous industry and product-specific standards have evolved. And there are some shown here on this slide. And examples of this would be ISO 26262 for automotive applications and ISO 138491 for equipment/machinery applications. One comment here is that standards typically tell you what to do, but not necessarily how to do it. Now, all standards have methods which are used to help estimate the risk of potential malfunction behaviours, resulting in a kind of risk assessment value. E.g., ASIL in automotive world is the result of assessing risk of malfunction behaviour. In aerospace, it's called DAL, or Development Assurance Level, but it's the same thing, the result of a risk assessment. In the industrial domains, you have SIL and performance levels, again, which do the same thing. In a similar way, requirements are common across all standards. They just use different names and properties. ASIL, DAL, SIL, etc. The basic idea, though, is to come up with useful requirements in functional safety for critical systems. All standards usually require you to create system architectures. Most refer to standardized modeling languages. In many cases, this is SysML. You have methods of testing the maturity of architectures in terms of hardware and software features. The use of FMEDA and fault trees is common across all industries. The methods are very similar across different domains. The application of these may be a bit different, but this is covered by the ANSYS Medini tool in terms of the usage of these methods, and I'll come on to that in a minute. Now, this slide illustrates the wide variety of functional safety analysis methods that are used in a functional safety project. The safety standards require us to perform all these methods in a consistent and formal manner. There are many good point tools available, but when using all these different tools, it's very difficult to achieve consistency, very time-consuming, and can be complex. All the while, there is requirement to share the project's approach and subsequent analyses through rigorous auditing. So this slide is about ANSYS Medini Analyze, and it streamlines functional safety analysis across the entire system architecture for safety-critical electronic control systems, including electronics down to the chip level. ANSYS Medini is a model-based integrated tool supporting safety analysis for safety-critical electrical and electronic and software control systems. It allows for consistent and efficient application of industry guidelines, especially tailored to industry standards. such as ISO 26262, 21434, 21448, ARP 4761 and 4754, MIL Standard 882, and ISO 61508 and 61511, and ISO 13849, and so on. Traditionally, several manual, typically Excel-type point tools are used for these functional safety and cybersecurity tasks. ANSYS Medini is an integrated solution for functional safety, reliability, and cybersecurity. It migrates data from other tools to preserve legacy work. It integrates with project version management and requirements tools, such as PTC Integrity or Windchill. It enables reuse and automation for assured consistency and traceability, providing checklist and project templates and reusable knowledge libraries. ANSYS Medini eliminates inconsistencies in the functional safety analysis, and the certification process is accelerated. Our clients advise us that they're achieving a 35 to 50% decrease in costs for functional safety analysis and a similar decrease in time to market. ISO 21434, which is the automotive cybersecurity standard, similar to the ISO 26262, specifies engineering requirements for cybersecurity risk management regarding concept, product development, production, operation, maintenance and decommissioning of electrical and electronic systems in road vehicles, including their components and interfaces. It offers an approach that prioritizes security throughout the entire life cycle of a vehicle. This means that those car manufacturers, but also OEMs, will need to display due diligence when it comes to the security of their software. In a very similar way to the earlier slide, which I was showing you about the point tool slide, Medini provides the integrated approach for working within the ISO 21434 environment. So I have a few case studies to have a look at here about how we've applied functional safety and provided solutions to our clients. There's a complex UK test facility at a client falls under the COMAR regulations and is classified as a lower tier establishment. This means that they are obliged to demonstrate that all hazardous scenarios have been identified and assessed to the competent authorities. And in this case, this was the Health and Safety Executive and the Environment Agency. After training the client's team in the technique of the Structured What-If technique, or SWIFT, Wild performed a series of SWIFT workshops covering the systems that comprise the test facility. The process drawings for the relevant systems were analysed and the information was recorded. The key findings from the workshops were documented within reports that were used to inform the facility safety report. And the benefits from all this was that by the training activities, we were able to maximise the input from those engaged in the SWIFT process. There was a better understanding of functional safety within the test facility team at the client. We were also able to illustrate to the competent authorities that the client was actually in control of issues identified. Now here's an ANSYS Medini application for a company that develops autonomous vehicle software. So Wild supported an autonomous software system company through their evaluation and deployment of ANSYS Medini to enable their functional safety engineers to be more effective and productive. The company was one of the earliest companies to test self-driving vehicles in public in the UK. And the company wanted to improve functional safety, efficiency and productivity, to develop a more robust functional safety and cybersecurity strategy, and achieve full traceability of functional safety and cybersecurity analyses. So the benefits from all this was that all functional safety and cybersecurity analysis methods in one integrated tool, they've gained 40% efficiency gains in productivity in complying with ISO 26262 and ISO 21434 by using ANSYS Medini. They're able now to get products quicker to market, and they have true end-to-end traceability, all through ANSYS Medini. Here's another user case for use of ANSYS Medini. There was a specialist vehicle engineering business was seeing a massive expansion in development of many new vehicle-mounted access platforms. They have 10 main designs in their range, but many variants with unique safety instrumented functions. Before the project, they were self-certifying their products using the ISO 13849 safety standard. But having developed a number of complex Excel spreadsheets in-house, they were finding errors and inconsistencies, and it was taking a long time to complete all the functional safety tasks. Weil provided an initial trial license of ANSYS Medini and then provided full functional safety support during the trial period. And the outcome of all this was that as they were able to share, to show they were going to improve their business, they were able to get a grant to help invest in the software. The client gained 45% efficiencies in terms of time and labour. They now have confidence in sharing their functional safety work with their clients. And there now is more efficient knowledge transfer when they move from project to project. And the final case study was on doing a SIL assessment of a railway depot personnel protection system. Depot personnel protection systems are installed in train maintenance facilities to control the safe movement of rail vehicles, protecting staff working in the vicinity. A manufacturer of such a system were looking to claim SIL 2 performance for their depot personal protection system, however, had no formal evidence to support this claim. Wild were engaged by the client to undertake a SIL assessment of their DPPS to confirm that every installation was following the IEC 61508 techniques and measures and could hopefully satisfy the functional safety requirements of SIL 2. We initially took a gap analysis to clarify the available supporting information and confirm project scope. We generated all documentation for the client. The initial work focused on new product hardware, but then grew to also include software and in-service systems. And from all the work that was done, we were able to demonstrate that they could claim SIL 2 compliance. This means that their equipment can now be put and marketed to be ahead of their competition that couldn't achieve SIL 2. It provides the client with a functional safety framework for future projects. But as important, or more importantly, it now opens up much more opportunity for new projects with their customers. So again, here's the takeaway image. Key takeaway points here are functional safety is becoming more important in products of all types, industrial and consumer. It protects users and the environment from harm. Its use and techniques applied vary from industry to industry. Cybersecurity is a significant growth area. A point tool solution is not efficient, encourages errors during data transfer and hinders the audit process. The ANSYS Medini tool is our tool of choice. It brings point solutions under one integrated umbrella. My final slide here is a very quick summary. That the functional safety and reliability engineering threads discussed today support and enhance the PTC product lifecycle thread. They remove siloed point solutions to fully connected enterprise database solutions, delivering significant efficiencies and achieving time to market and cost efficiency gains of up to 50%. Thank you for listening.
Excellent. Thank you for a great presentation, Simon. So now it's time for a little Q&A. So we have our first question here. It is from Onder. He is of the opinion that, in fact, reactive failure correction may be related with reliability in his view. Why do you say it is not?
I'm talking about best practice here. There are going to be many instances where you get unexpected failures. What I'm trying to promote here is that to be the most effective reliability engineering techniques is to get as much reliability engineering work done up front early on in the concept and early design phases. But you're right, reliability engineering does play a part in the reaction side of things. It's just that we try and engineer some of these things out as early on as we possibly can. I hope that answers the question.
Oh, we got a thumbs up, so I think that sounds
Phew.
So let me see. The next question is, how does reliability, DFR, differ from traditional approaches to reliability engineering?
It's really because it comes back to what the person before was asking about. It's more about traditionally some techniques were used once the product had been built or was in operation. Where the DFR aspect comes in, it comes back to getting all the reliability work done right early on up front, trying to keep costs down. There's the old adage that the longer you are in the design phase and there are design changes to be made, the more costly it is to make design changes the nearer you are to production. So the earlier we can get into the design cycle, the reliability engineering work, the better. So that's where the DFR bit makes a difference. It's proactive.
Okay, and the next question is, how can organizations measure the effectiveness of their reliability APM efforts?
Okay, well that's a good question. One way to measure the effectiveness, I suppose, of APM is to track your key metrics. So things like mean time between failure, or MTBF, or some people use mean time to repair, MTTR. And by comparing these metrics over time, you can start evaluating the effectiveness of their reliability APM efforts, and perhaps identify areas for improvement. So yes, it would be metrics such as MTBF and MTTR would be a good way of doing that.
And we have time for a last question. So, what is the difference between safety integrity level and performance level, and why?
And why? Okay,
And why have
why?
two
Yeah.
methods? Oh, sorry, I missed the end. And why have two methods?
Oh, right. Okay. Well, different industries have adopted different standards over the years. So the process industry typically uses IEC 61511, which is just an offshoot from 61508, when defining safety instruments and systems, or SIS. And they use SIL, SIL 0 to SIL 3. Machinery safety have adopted ISO 13849, where PL is used, and they use A to E rather than numbers, they use letters. So SILs and PLs broadly map to SIL 0, and PL through to SIL 3. So those would be my suggestions, that they have two methods. It's the way the industry has developed over the years.
Okay, excellent. So that was it for this time. Thank you so much, Simon, for this fantastic
Thank you.
presentation.
My pleasure.
And we will be back for more next year. So happy holidays, everybody. And
Happy Christmas, everybody. Thank you.
Thank you. Bye.